Why can some communication systems carry huge amounts of data while others are limited to much lower speeds? The answer often comes down to a single concept: bandwidth. Bandwidth determines how much frequency space a signal occupies and plays a fundamental role in nearly every RF and communication system. Every communication signal occupies a certain range of frequencies. Whether it is a radio broadcast, a Wi-Fi transmission, a radar pulse, or a satellite signal, no real signal exists at only one frequency. Instead, signals spread across a portion of the frequency spectrum. As communication systems become more advanced, engineers constantly face the challenge of fitting more users and more data into limited spectrum resources. The radio spectrum is finite, and multiple systems often need to share it efficiently. Understanding how much spectrum a signal requires becomes critically important. The problem is determining how much frequency space a signal occupies and how this affects system performance. Engineers need a practical way to measure and manage spectral usage. This leads directly to the concept of bandwidth. Bandwidth is the range of frequencies occupied by a signal or passed by a system. It is usually measured as the difference between the highest and lowest significant frequencies present in the signal or system response. For signals, bandwidth describes how much spectrum is needed to transmit information. A narrowband signal occupies a relatively small frequency range, while a wideband signal occupies a much larger portion of the spectrum. For systems such as filters and amplifiers, bandwidth describes the frequency range over which the system operates effectively. Frequencies outside this range are often attenuated or rejected. As a result, bandwidth serves as a fundamental measure of both signal characteristics and system performance. Intuitively, bandwidth can be compared to the width of a highway. A narrow road can accommodate only a limited number of vehicles at a time, while a wider highway can support significantly more traffic. Similarly, larger bandwidth generally allows more information to be transmitted. Physically, consider two communication signals. A simple voice signal may require only a few kilohertz of bandwidth, while a modern Wi-Fi signal may occupy tens or even hundreds of megahertz. The wider bandwidth enables much higher data rates and more complex communication capabilities. Mathematically, bandwidth emerges naturally from Fourier analysis. Signals containing rapid transitions or sharp edges require many frequency components to represent them accurately. As signal complexity increases, the required bandwidth generally increases as well. Bandwidth is one of the most important design parameters in RF engineering. Engineers use it to determine spectrum allocation, channel spacing, filter specifications, and achievable data rates. Nearly every communication standard includes strict bandwidth requirements. In wireless communication systems, bandwidth directly influences capacity. According to fundamental communication theory, wider bandwidth generally allows higher information throughput. This is one reason why modern technologies such as 5G utilize larger bandwidths than many earlier communication systems. At the system level, bandwidth affects transmitter design, receiver sensitivity, filtering requirements, interference management, and spectral efficiency. Understanding bandwidth is essential for designing reliable and efficient RF systems. Although larger bandwidth often provides advantages, more bandwidth is not always better. Wider signals consume more spectrum, may create additional interference challenges, and often require more sophisticated hardware and signal processing techniques. A common mistake is assuming that bandwidth and frequency are the same thing. Frequency refers to where a signal is located in the spectrum, while bandwidth refers to how much of the spectrum it occupies. Two signals can have the same center frequency but completely different bandwidths. The bandwidth concept forms the foundation for many advanced topics in communication systems. Understanding bandwidth prepares engineers to study filtering, spectral efficiency, modulation techniques, and channel capacity in greater depth. In this lesson, we learned that bandwidth describes the range of frequencies occupied by a signal or supported by a system. We also saw how bandwidth affects data transmission, spectrum usage, and overall communication system performance. In the next lesson, we will explore filtering signals and learn how engineers control and shape signal bandwidth using filters. If you found this useful, like the video, subscribe, and follow for the next lesson.